In the previous video, we discussed the basics of the trapdoor function with elliptic curve math. In this video, we will go over elliptic curve multiplication. This is what gives the capital K public key and the lower k private key that mathematical link. Again, we won't get into all of the details of elliptic curve multiplication because it's not necessary for our purposes, but the next few slides will cover the basics so you can conceptualize what the computers and what Bitcoin wallet software is doing when they're running elliptic curve math and elliptic curve multiplication. Two key elements to elliptic curves that enable their trapdoor functionality are the following. Number one, they are symmetric over the x-axis, meaning any point on the curve can be reflected over the x-axis and remain the same curve. Number two, a straight line will intersect the curve at most 1, 2, 3 times. Again, a straight line will intersect the curve at most 1, 2, 3 times. These two elements are key to understanding elliptic curve multiplication and understanding how the public key is derived from the private key. But before we dive deeper into elliptic curve multiplication, let's first talk about elliptic curve addition. So in this example taken from the website at the bottom, I want to give them full credit. We will discuss adding points P plus point Q. So we begin by drawing a line called L through P and Q. This results in a third point along the curve, R. Remember, like I just said, a straight line will intersect the curve at most 3 times. So here's that visual representation of that. Line L intersects the curve at points P, Q, and R. Next, the first rule we discussed comes into play. A point along the curve can be reflected over the x-axis and remain along the same curve. And this results in a new point called the sum of P and Q, denoted by the plus sign with a circle around it. In essence, adding points P plus Q together results in a third point, sum of P and Q. Again, Bitcoin's blockchain uses elliptic curve multiplication instead of addition. Remember, generator point G times the private key results in the public key. So it's generator point G times the private key, not added. Multiplication is really just saying a number added to itself a number of times. Same thing with elliptic curve multiplication. By multiplying a generator point by a number, you would really be adding that generator point to itself. And in elliptic curve math, when you add a point to itself, the resulting line is the tangent line at that point. So again, we have line L. And like I just said, since P is added to itself, or multiplied by 2 in this situation, line L is the tangent line that intersects the curve with point P. Again, we get a point R here. Now, I know it's supposed to intersect the curve at most 3 times. And if you think about it, we added P to itself. So this is technically 2 points. P plus P gives you this. R is that third point. Again, just like with the addition, we reflect it over the x-axis, and you are left with 2P. So P times 2 gives you this point here, 2P. So this makes complete perfect sense to you, right? No, I'm just joking. I know it's confusing. We're touching on stuff that you've never seen before, but as long as you can grasp the basics of what I'm talking about so far, especially with the tangent line aspect and with the reflection aspect, then moving forward, you'll understand what I'm saying. So let's say I make it public knowledge. This is me. Let's say I make it public knowledge that I'm using Bitcoin's SECP 256K1 curve. And I also make the coordinates of the generator point public knowledge. Since you are a cryptography expert now, this is you. You know the trapdoor function of that curve to be capital K equals lower k times g. I also let the public know the coordinates of the final points of my public key. I then announce a challenge in which I will give $1,000 to the first person that could tell me the private key I used to arrive at that public key.